Okay, sorry, I got a little bit distracted. In the first video, it was supposed to take a little bit longer. Something needed my attention. So I'm back. So I was trying to say that you realize that when you look at this left hand side, the whole of the left hand side can be written simply as just the product xy, the whole of it being differentiated with respect to x. So we are now replacing the left hand side x dy plus y dx with the expression d dx into brackets xy, because you realize that when you differentiate this product xy, this is what you are going to get. Because first of all, you have x as the first one, then differentiate the second variable. So we have x dy plus now the second one this time y, then differentiate the first variable, which is in terms of x, then dx equaling to 0. So that means instead of having equation 1 with this form, then you can write it as d dx of xy equaling to 0. Then when you cross multiply both sides here, you remain with d into brackets xy equaling to 0 dx. And when you integrate both sides, because whenever you have d of x and you integrate it, you always remain with x. I think that is clear from your A-level mathematics. So from here I realize that you have integral d of xy. When you integrate d into brackets xy, you remain with xy equaling to integral of 0 dx. What do you get when you integrate 0 with respect to x? That means you have 0 times, here x is power 0, so when you add 1 x to power 0 and then divide by the new power, since you have 0 here, everything will be 0, so you shall only remain with a constant on the right hand side. So we end up with xy equaling to c. So you can see that we've been able to solve this kind of equation, which is in this form, just by using the fact that if you look at the left hand side, it can be written just simply as under one differential. Okay, and then when you do the cross multiplication, the numerator, which is d of xy, if integrated, gives us the function in the bracket. So the same applies to this second example. In the second example, let me first put it up slightly. Okay, so it's becoming stubborn. Okay, I think here it's better. So in the second example, we have 2x squared y dx equaling to 3 minus 2xy squared. Okay, so this equation, realize that if you do the cross multiplication and the simplification, we can write it in this form. Okay, now this time I'm not equating it to 0 because there's something that I want you to see. So I want you to try and differentiate. Okay, let me put the pen. If you have a function x squared y squared, if you were to differentiate this function with respect to x, okay, and remember it has two variables, so that means if, for example, you consider x squared and then you differentiate y, that means you have 2y, okay, you have 2y. Since we've differentiated y, that means you shall have dy. Then plus. Now, so first we maintain this and differentiated this. Okay. Now, second, let's differentiate the x and maintain y. That means we shall have 2x y squared. We've differentiated x, so we shall have the x. Okay, and realize that this expression is the same expression that we have here. So realize that if you do away with the 3 and then remain with this term on the left hand side, this term on the left hand side is simply d of x squared y squared. And then when you equate it to 3x and integrate both sides, then you're going to end up with x squared y squared equaling to 3x plus a constant. Okay? Okay. So, what are we trying to say? I'm trying to put it. Oh, I didn't stop the pen. Okay. Yes, it has moved. So, what are you trying to say? So, that's what now this next sentence is trying to illustrate, that we are able to solve these two equations, differential equations, because their left-hand side expressions were reducing to total differentials. So total differentials here means that if you look at a function, for example, a function like this, can you be able to write it with a differential? Like there we've done it here, we've said that d dx of xy. Then this other function here, this one, this one, okay, it's becoming stubborn. But this other function here, we are also able to write it as a total differential, and we say that the whole of it, this left hand side, can be written as d of x squared y squared. Okay, so using that property, we are able to find solutions to these two differential equations. Now that leads us to our next definition. But how can I rub this? Okay, I've rubbed it. So that leads us to our next definition. And we are saying that a first order differential equation whose left hand side expression can be easily regrouped into total differentials is said to be an exact differential equation. So now we are adding a new definition, an exact differential equation. If you have a differential equation whereby the left hand side, you can be able to write it just as a total differential. You have d dx of something, and when you differentiate that, you realize that what you get is what you're having in that differential equation on the left hand side. Then in that case, we say that that differential equation will be exact. Okay, so we have one interesting property here, that the first order differential equation m xy dx plus n xy dy is equal to 0 is exact. So remember, at first we looked at examples where we are dealing with such equations. Okay, now when are we going to have such differential equations equaling to 0 being exact? So the condition is that this form of equation will be exact if curly m, curly y, I always pronounce it as curly m, curly y to mean that partial derivative of m with respect to y is equal to partial derivative of n with respect to x. Take the difference here. In the equation we have m dx plus n dy. But when you are testing for this condition of exactness, we instead differentiate m with respect to y and we differentiate n with respect to x. So for it to be exact, if it is in this form, then these two expressions must be equal. Okay, and I have the proof here. I'll briefly go through the proof, then you also go through it step by step and make sure you understand each and every concept. So since we already are showing an equation, a first order differential equation of this form, so we shall also assume that this equation here is exact. Now, if it is exact, that means we want to show that partial derivative of m with respect to y, what you get is the same as partial derivative of n with respect to x. I'm now looking at this definition. That is what we want to show, that this derivative and this other partial derivative will be the same. Okay? Now, since this is a differential equation, that means it has a solution. And that solution is what we are calling this function. Of course, the solution, since this is a differential equation with two variables, that means that its solution will also have two variables. So that's why we are saying that there exists a function f of x, y. Okay? And such that this function, when you differentiate it with respect to x, we get m of xy. So I'm now trying to relate this in a way that differentiating f with respect to x, okay, then that is what will give us the m of xy, because m corresponds to the x, and differentiating f with respect to y, that's what gives us n, because it is n that connects to y. So these are just if you're dealing with derivatives in more than one variable, I think you should go and read about that just to remind yourselves. Okay? Yeah. Now, also remember that if you have a function in two or more variables, for example, a function f of xy, then this function f of xy can also be written in this form. Still on this, I refer you to your backhouse knowledge from A level. Okay, so we have that df of xy. So take the difference. This is df of xy is the same as partial derivative of f with respect to x dx plus partial derivative of f with respect to y dy. Okay? Okay. Now, what will be the partial derivative of m with respect to y? So, remember from the definition, let me take you back. We want to prove that partial derivative of m with respect to y is the same as partial derivative of n with respect to x. So now we want to find partial derivative of m with respect to y. Then after, we shall get partial derivative of n with respect to x. If these two are equal, then we shall conclude that an equation of this form is exact. Okay, so let's start and see how it goes. So we're here, partial derivative of m with respect to y. This can be written as, if you first put the m in brackets, maybe let me first get a pen here. So you're saying that this can be written as partial over partial y into brackets m. Okay, but what is m? M, we've said here, that is partial derivative of f with respect to x. So we shall put this in here. That's why you have this step. And when you expand this, you get partial derivative of 2f over curly x curly y. Then we do the same for partial derivative of n with respect to x, because you want to find out whether this partial derivative and this are equal. So how will you define this? This will be the same as partial curly over curly x into brackets n, which is curly f curly y. Okay, and then when you expand this, you get curly squared f over curly x curly y. So you can see that, okay, here we are having curly squared f over curly x curly y, and what do we have here? Curly squared f over curly x curly y. So the two are equal. Okay, so that's why you have that. Hence curly m curly y is the same as these expressions, which is also the same as curly n curly x. So that means that if a differential equation in this form is equal to 0, then it is exact if and only if this partial derivative of m with respect to y is the same as partial derivative of n with respect to x. They can give you a differential equation which is in this form, and they ask you to show that it is exact. So that means you'll be interested in finding out whether when you differentiate m with respect to y, what you get is the same as differentiating n with respect to x. Okay? Yeah, now in the next video, I want us to start looking at solving these exact equations. Okay, let me see. Yeah, so I'm going to first stop this video from here, and then I'll start a new video. So we're going to start from here, how to solve an exact differential equation in this form. So the mere fact that it is exact means that curly m curly y is the same as curly n curly x. That's what we've just looked at. Okay, so see you in the next video.